This is the third recording for regression. This will be topic 7, okay? So first this is the deviation of y. So how will we calculate sums of squares total, which is just the sum of all deviations, square deviations of y, right? So let's walk through it. The sum, first we have to calculate the sum of y, which is 1 plus 3 is 4, 8, 10, 16, 21, 28. Okay, this is the mean of y. So n equals 7, right? 1, 2, 3, 4, 5, 6, 7. So 28 divided by 7 is 4, right? Then we have to calculate the deviation. So the deviation is just always 1 minus, it's just the score minus the mean, which is 4. So 1 minus 4 equals negative 3. 3 minus 4, oops, equals negative 1. 4 minus 4 equals 0. 2 minus 4 equals negative 2. 6 minus 4 equals 2. 5 minus 4 equals negative 1. And 7 minus 4 equals 3. Now, if you want to make sure you got it right, you can add these up and it should equal to 0. So let's see, negative 3 cancels out, negative 1, negative 1. 5, oh, this is positive 1 right here. See, I found an error. 5 minus 4 is not negative 1, it's positive 1. Always check them, right? Let me get my little pen again. Pen. Okay, oops. I'll get rid of this little draw. Here we go. Pen. I lost my pen. Okay, so this adds up to 0 now. That's wrong. I can't figure out how to get my pen back, guys. Line, font, text, select, mouse, stamp. I want the eraser. Still got the eraser. Bear with me, everyone. I'm trying to figure out how to do this. Okay, so now we have to have the square deviation. So negative 3 times negative 3 equals 9, right? Negative 1 times negative 1 equals 1. 0 times 0 equals 0. Negative 2 times negative 2 equals 4. 2 times 2 equals 4. 1 times 1 equals 1. And 3 times 1 equals 3 times 9 equals 9, right? So then we have to add these up to get the sum of the square deviations. And this is just 28, which is never going to happen. You're going to have the sum of y and the sum of the square deviations be the same. This is total coincidence, but it is here. So 28, right? This is the sum of squares. This should all be familiar. This should be in kind of a refresher for calculating. So you start calculating the standard deviation or the variance with this little chart that I have here, this little table, right? So moving on. So proportion of variance accounted for. So not using a relationship, as I said, we always use the mean of y to predict y values. And this is from your textbook. I like this little graph. So phones per hour, right? Here the mean of y is 4. So if all we have to predict how many phones per hour is the mean, then we'd predict mean. Okay, so what if we're predicting it by assembler test scores, right? Then we can predict it from the regression equation. This is the line of best fits or the regression line, okay? So we can use y prime to predict it. So here we have a much better prediction, right? Compared to 4, right? You get much better predictive value using the regression line. And the difference between using the mean of y versus using the regression line is an idea of how the proportion of variance accounted for works. Okay, more sums of squares. So sums of squares total, we can divide up into 2 different types. Sums of square regression plus sums of squared error. Sums of square regression is just the difference between y prime and the mean of y. So that's that increase in predictability. So how much better does y prime predict than the mean? And then you square them. Okay, that's also called sums of squares explained by the regression equation or model. This is the good stuff. We want this to be as big as possible. It's how well the model, the regression equation, fits the data. Okay. Sums of squares error just refers to the square differences between the actual value of y and the predicted value. So these are all the values of y that are not right along the regression line. So that's the difference between them and the regression line. Okay, this is also called sums of squared residual. In fact, that's how SPSS refers to it. The term residual, when we're talking about statistics, is all the unexplained variability or in the data that's not accounted for by the model you're using. Also called unexplained variance, variability in the criterion that cannot be explained by the predictor. Okay, the square root of the sums of squared error is the standard error of the estimate, which you really don't need to worry about now. Anyway, so let's look at this in a bit more detail. Sums of squared regression is just the difference between the predicted value of y, so the regression equation, and the mean of y squared, okay? There's our regression line, and there's the mean, right? So all these differences, this is y prime minus the mean of y. Okay, this is a weak relationship, so there's not a big difference there. All right. Sums of squared error is the difference between the actual values of y and what would be predicted by the regression equation. Again, and this is pretty big because this is a weak relationship. We can see there's big differences here, right? So what about with a strong relationship? Okay. Here we can see this slope is much greater and it's a better relationship. The relationship between cognitive flexibility on the x-axis and happiness on the y-axis. So there's the mean of happiness, right? And these are all the differences between how well the mean would predict it and the regression equation, the green guys, okay? That's the good stuff, sums of square regression or explained, okay? This would be the sums of squared error, right? The difference between the actual values of y and the regression equation, right? There's still a lot there, but it's less. There's the regression line. That's where it's exactly lies in the regression line right there, right? So there's some values where it's perfectly predicted. So SPSS actually outputs the sums of squares, all right? Here is r squared. So r squared is calculated by dividing sums of squared regression, which is the good stuff, everything that predicts the increase in predictive ability we get from using the regression equation. So y prime minus the mean of y. Divide that by the sums of squared total, and that gets the proportion of variance explained. Here's the SPSS output for sums of squared regression and sums of squared error. And then, of course, the total, which just you add them up, right? So for simple linear regression, like we're doing, just using two variables, r squared is the same as Pearson's r squared, and it's called the coefficient of determination. Again, the standardized slope is the same as the correlation coefficient. Multiple regression is what you call it when you use more than one predictor variable. So for example, we might say, does cognitive flexibility lead to greater happiness? Which is kind of almost causal language. So maybe you should say, is cognitive flexibility related to greater happiness? Because maybe being happy makes people more flexible, right? Both things probably happen, right? If we do a scatter plot and add a regression line, we can see that regression line right here. Y equals 21 plus 1.04x, right? We saw that before. If we do our correlation, we see it's a pretty strong correlation, 0.458. And then we can also use regression. And we can see the slope right there, right? We can see the standardized slope, which is the same as the regression coefficient, right? And R, if there's only one predictor variable, okay? We can also see R squared is 0.209. You can see the sums of squares as well. This is all your regression output. Okay, here's the regression line. There's the intercept, slope, and the regression line. Okay. And that is also what is outputted by default when you do a scatter plot and add the regression line. So you can always check your work. All right. So for example, how happy can we expect someone who scored 60 in cognitive flexibility at time 1 to be in 2 weeks later? Oh, okay. So I guess I did collect this data separately. So we could a little bit talk about causality, but it's not an experiment, so not really, right? Okay, so if we plug in 60, we get 83, right? So there's an x equals 60, goes to about 83 happiness, right? Okay, so that's about it. Just a few more slides. Remember, here's the formula for correlation. We have the covariance of xy divided by the standard deviation of x times the standard deviation of y. Reminder, the standard deviation. Okay, we're using the estimated population value here. Okay, so formula for a regression line, and you absolutely do not have to calculate these for this class, but it's really useful to understand what's going on. Okay, we just see that A is the mean of y minus the slope times the mean of x. Okay, the slope is just the covariance of x and y divided by a standard deviation, divided by the variance of x, right? Is estimated variance of x, which is right here, which we've already seen. Formula for sums of squares, we've already gone over, right? So if there are any questions, please post them in the FAQ.